Once again, good morning to all of you. And today we will discuss the topic like a sharing bridge. In the last lecture, we have discussed the bridges like a Maxwell bridge, and we have done the numerical of the Maxwell bridge. Okay, but today we will discuss the topic that is the sharing bridge. The sharing bridge is used to maintain the value of the capacitor basically. Okay, means this is the AC bridge, and this bridge is used to measure the value of the capacitance of the capacitor. Okay, and the dissipation factor and property of the insulator, capacitor, bushing, and the other insulating material. Basically, again I am repeating, this bridge, sharing bridge, we are using to find out the value of the capacitance, capacitor capacitance. Okay, that we can say, also say that the capacitive reactance, we can find out the capacitive reactance of the capacitor by using this sharing bridge. And this sharing bridge is working on the AC supply, that's why it is called the AC bridge. Next, we are having a like a, this is the circuit diagram of the sharing bridge. First arm, that is the arm A to B. This arm is called the, this arm consists of the capacitor C1 and the resistance R1. Okay, this is consists of the capacitance C1 and the resistance R1. And the B or C resistance, it is consist of the resistance only, R3. Okay, and then we are having the arm AD. It consists of only capacitor C2. Okay, then we are having a arm CD. In this arm we are having a, again we are having a one more capacitor, C4 capacitor, and R4 resistance. These capacitor is called the variable capacitor, means arrow is in this capacitor. That means this capacitor is the variable capacitor, and this resistance is also called the variable resistance. So this is called the variable capacitor and variable resistance, whose value is known to us. Okay, so basically in the sharing bridge we will find out the value of the C1 and the R1. Okay, students, we will find out the value of the C1 and the R1. That is the arm AB. Rest values are known to us. Okay, so it, this bridge is working on the AC supply. Here it is the AC supply is given to this bridge, and across the B and D we are having a detector. Okay, across B and D we are having a detector. Detector is showing the null indication. Okay, the detector is showing the null indication, and this supply is the working, the bridge is working on the AC supply. Okay, so these are the parameters of the sharing bridge. Means C1 capacitor whose capacitance is to be determined, or whose capacitance we have to find out, that is the C1 capacitor. Okay, then we are having a R1 resistance, means R1 resistance means whose resistance we have to find out. Then we are having a C2 as the standard capacitor, means whose value is known to us, and it is free from the losses. This capacitor is free from the losses. And then we are having a R3, that is the non-inductive resistance, whose value is also known to us. And C4 and R4 are the variable capacitor and variable resistance. Why we are taking this variable capacitor and variable resistance, students? Because when we are changing the values of the C4 and the R4, we are getting the null indication. Means when we are changing the value of the C4 and the R4, we are changing the values of from the knob for the capacitor C4, we are changing the value of the resistance R4. Then the null indication will be shown on the on the detector part. Okay, students. So this is the brief about the this bridge. Next, like we are applying the balance condition of the bridge. The bridge is when bridge is balanced condition means by when bridge is balanced, when the galvanometer is showing the zero indication, when our detector is showing the zero indication, means our bridge is balanced. Okay, student. So when our bridge is balanced, then we will apply this equation of Wheatstone bridge that I have repeated in the last lecture. Z1, Z4 is equal to Z2, Z3. Means Z1 and Z4. These are the impedance of the opposite arm. Okay. These are the impedance of the opposite arm. Similarly, Z2 or Z3 are the opposite of the impedance of the opposite arm. So we are putting the values of Z1, Z4 and Z2 or Z3. Then we are equating the real or the imaginary part. Then from the equation 1, we are finding the R1 value and we are finding the C1 value. So this is the basically like a basic values of the unknown resistance and the unknown capacitance. Means by using this values, we will find out the values of the unknown resistance or the unknown capacitance. So sharing bridge is our our AC bridge that is used to measure the value of the capacitance C1, where C1 is the unknown capacitance and C1 value is equal to C2 R4 divided by R3. Means C2 is the known value, R4 is also the known value, and R3 is also the known value. So by putting these values in the equation number 2, we will find out the unknown capacitance. Then this is the phasor diagram of the sharing bridge. We will draw the phasor diagram like I1 R1 is this one. Basically, it is showing by this line. Then we are having a I3 is equal to I1 R3. Then I4 is equal to, that is our resultant vector that is showing by this dotted line, IC upon omega C4. That is shown by this one because capacitor always capacitor voltage always lag behind the current by some angle. So we will find out the dissipation factor D1, that is the tan delta. Tan delta is the omega. This is the delta basically angle. Okay. That is called the dissipation factor. That is the omega C1 R1. And this is the omega. We will take a C1 R1 values, that is the C2 R4 upon R3. We will multiplying these, putting this C1 value or R1 value, that we will find out by using the equation Z1, Z4 is equal to Z2, Z3. Then dissipation factor is come here. Actually, the numerical came on this dissipation factor, that omega is equal to C4 and R4. Means by putting this value, we will find out the dissipation factor. So this is the one numerical that is based on this sharing bridge. Means we have known these values R1, R2, C1 and C3. Then these values are given in the numerical part. So by putting these values in the Rx or Cx, we will find out the value of the unknown resistance or the unknown inductance. So these are the values of the resistance and the capacitance. So, so we will write down Z1 is equal to R1 plus 1 upon j omega C1. This is the impedance of this arm. Okay. So next we are having a Z2. Z2 means we are in the Z2 we are having only the value of the capacitor C2. Okay, so Z2 we will write down 1 upon J omega C2. Okay, Z3 is the only resistance R3. We will write down the R3. Similarly, Z4 is the capacitor C4 and the resistance R4. It is in parallel. We will write down it as the like the so these two C4 and R4 is parallel. So it is, we will write down it C4 and the R4 are in parallel. So we will write down its impedance as the R4 upon 1 plus J omega C4 and the R4. This is the impedance of the Z4. So we are getting Z1, Z2, Z3, Z4. Okay. This thing we have done in the last lecture also. First of all, we will find out the impedance of the each arm Z1, Z2, Z3, Z4. Okay. Now we will use this equation Z1, Z4 is equal to Z3, Z2. We will put the values here in this equation Z1, Z4 is equal to Z2, Z3. So when I am putting this value here, we are getting the R1, Z1 value is the R1 plus 1 upon J omega C1. Okay, beta. Then Z4. Z4 value is this one. R4 upon 1 plus J omega C4 R4. Okay. We are getting these two values. This is equal to R Z3 is the R3 and Z2 is the 1 upon J omega C2. Okay, so we are having this equation last. Okay, now we will solve this equation. We will do the we will do the multiplication in this equation and then separating the real or the imaginary parts. So like then we will separate the real and the imaginary parts. Then we will solve this equation. How to solve this equation? I will solve the rest of the part also. Suppose this is the R4. We will write down R1 plus 1 upon J omega C1. Then this is the R4 will multiply it by this one. This is the R3 J omega C2 1 plus J omega C4 R4. This thing we will write down along the right side. Now we will do the multiplication. Okay. Then we are having a like a R1 R4 plus R4 upon J omega C1 is equal to R3 J omega C2 plus R3 C2 C4 R4. Okay, we are getting this equation. So then you can solve this equation. Okay, this is the iota. If I am multiplying here iota and below iota, it will become my iota square. So iota square is equal to minus J R3 upon omega C2. Like we will write down like this equation as iota form. Okay, means if the iota is in the denominator, we will eliminate the iota from the denominator by using this technique. We will multiplying the iota with the j. We will say iota as the j. Iota square is equal to minus 1. Means the j square is equal to minus 1. We are using this identity and we will eliminate the iota from the denominator and we will write down this equation as we will write down the equation as R1 R4 plus, sorry, here we will write down the negative sign. This is the J R4 upon iota C1, because here I will multiply iota with the numerator and with the denominator. It will become my iota square, and iota square is the -1. So it is the minus J. So next we are having a like a minus J R3 upon omega C2 plus R3 C4 R4 divided by C2. Now separating this real part with this real part. This is the real part. This is also real part. This is the imaginary part. This is also the imaginary part. Okay. So from the imaginary part, we will find out the value of the C1, and from this real part we will find out the value of small r1. Okay, from this real part we will find out the value of the small r1. Okay, from this imaginary part we will find out the value of C1. Okay, so by separating real part with this real part, imaginary part with this imaginary part, we will getting the value of the small r1 and the capital C1. So when we are separating this real and the imaginary part from this equation, we are getting R1 is equal to R3 C4 upon C2, and similarly C1 is equal to C2 R4 divided by R3. So this is the value of the unknown resistance. This is the value of the unknown capacitance. So this thing is clear to everyone or not?
सर
Yes,
क्लियर है
sir.
क्लियर
Clear है.
Any doubt to any student? Okay, students, these values are known to us. R1 value is known, C1 value is known, R2 value is known, C2 value is known. So we will put these values, and we are having the formula Rx is equal to R2 C1 by C2, and Cx is equal to C3 R1 by R2. So according to that, we have to put these values in this formula, and you will simply find out the value of the unknown resistance and the unknown capacitance. So we will put the values here. R2 value is the we are having a R2 value is the 100 kilo ohm. So we will write down 100 into 10 to the raised to power 3. Kilo ohm means 10 to the raised to power 3. We will write down 100 into 10 to the raised to power 3. And microfarad, like C1 value is the 0.01 microfarad. Microfarad means 10 to the raised to power -6. We will write down the 10 to the raised to power -6 divided by, again we will having a 0.1. C2 value is the 0.1 microfarad. 10 to the raised to power -6 farad. Okay, so by using this value, this 10 to the raised to power -6 cancel out with this one, and we are having 100 and 10 to the raised to power 3. By solving this equations, we are getting like 100 kilo ohm value is the Rx value. Similarly, we will find out the value of the unknown capacitance. Simply put the value of C2, R1 and the R2. And students, don't be confused with here don't be confused with the this diagram that key in the diagram you are having a C1 here, R1 here, we are having a R3 here, C4, R4 is here, C2 is here. So in the question you will given the values like R1 is the, like they in the numerical they will say that the only resistance, the resistance between the arm A and B is the 470 arm. So that means this is equal to R3. This thing is given in your numerical part. Okay, don't be confused with means like जो सर ने पढ़ाया है उसमें that in that part R1 is shown here. Okay, but there was a note R1 in that diagram, so don't be confused with that one. Okay, so simply in the numerical part it is given that R1 is the resistance between the A and B and C is the value of the capacitor and the parallel resistance. So the value of the parallel capacitor and the resistance is this one. So these things are given in the numerical question. Okay, so don't be confused with that part. Okay, so this numerical is clear to everyone.
Yes, sir.
In our Anderson bridge, we will find out the value of the inductance by comparing it with the value of the known capacitance value and the known resistance value. So we will find out the value of the unknown inductance. Okay, so unknown inductance value is known, find out with the help of Anderson bridge. So in this circuit diagram, we will find out the value of the L1 and the resistance R1. Okay, we will find out the value of the L1 and the R1, and rest values are the known to us, means the rest component values R2, R3, R4, small r, C. These values are known to us. So this is the circuit diagram of our Anderson bridge, and this diagram is slight typical as we compare it with the other bridges. So this is the very important bridge. Okay, this is used to find out the value of the inductance or the resistance between the arm A and B. In the arm A and B, we will find out the value of the R1 and the L1. Okay, students, we will find out the value of the R1 and the L1 by comparing it with the value of R2. This is the capacitor, this is the resistance, this is R3, R4 resistance. So this is the diagram of the Anderson bridge. Okay,
Hello, sir.
In the Anderson bridge, we will connect the detector that is between the B and E. Okay, in the other bridges, we are having a detector or a galvanometer either to the point B or to the point D. But here we are having a detector between the point B and E. Okay, students. So here one more capacitor is attached between the point E and C, that is the capacitor C. Here we are using the variable resistance, that is the small r resistance. Here we are having a R4 resistance, R3 resistance. So this is the diagram of the Anderson bridge. Now what we are doing here, like in the Anderson bridge, we are converting this diagram into the simplified diagram. Okay, students, we are converting this diagram into the simplified diagram with the help of star delta connections. Okay, these star delta connections you have learned in the BEEE. Okay, so we are converting this diagram. This is a little bit complex diagram. So we are converting this diagram into the simplified diagram with the help of the star delta connection. So this is the simplified diagram. The figure number 12.9 is the, this is the simplified diagram of the above diagram, and this is the star delta connection which we are using here. So with the help of star delta connection, we are converting this diagram into the simplified diagram, that is the Maxwell inductance capacitance bridge. Okay, students, in the last lecture, we have done the Maxwell inductance capacitance bridge. So we are converting this diagram, this complex diagram into the simplified diagram by using the star delta connection. So how to convert this star delta connection? Again, I will explain you. So we are having a diagram here. So in this diagram, we are having like this one is the our resistance. Then we are having our inductor. Okay, these values we have to find out. R1 values or L1 values we have to find out. Then we are having this R2, that is the known resistance value. Here we are having our R3 value. Sorry, this is the R3 value. This is also the known value. Then this is the R4 value that we have to this is also known value. We have to find out the R1 and L1. So this is the detector we are connecting, and this is the capacitor we have connected. Okay. So one more resistance between this point is the small r resistance, that is the variable resistance. This is the variable resistance. This is the capacitor C. Okay, so the supply here I am giving, this is the AC supply. Okay, so I am converting this diagram into the simplified diagram, that is the like a Maxwell bridge, Maxwell capacitance bridge diagram. Okay, so what is the Maxwell capacitance bridge diagram? Here we are having a resistance part. Okay, then so I am converting it into the simplified diagram. This is the capacitance, this is the inductor, and again here we are having a resistance, and in the center we are using again one more resistance. Here we are having a resistance, and this is the resistance. Across this resistance we are having a capacitor, parallel capacitor. So this is the simplified diagram. We are converting this diagram into this simplified diagram. Okay, so this is our simplified diagram. How we are converting this diagram into this simplified diagram? With the help of the star delta connection. Okay, so with the help of the star delta connection, we are just converting this complex diagram into the simplified diagram, that is the Maxwell inductance bridge diagram. Okay, students, so how we are converting, I will explaining you. So kindly see your screen, students. We are finding the value of the R1 and the L1. Okay, so we have to find out the value of R1 and the L1. Then okay, we will find out the value of the R1 and the L1. So like next we are taking this star delta connection. See this, students, this is the value of the R4, R3, and this R resistance. So we are converting these three resistance, R3, R4, and small r. Check this. This is the R3. Okay. This is the R4 and this small r resistance. They are making the star they are making here, they are making the, this one is making the star connection. Okay, R3, R4 and small r and this capacitor are making the star connection. Okay, so we are converting this star connection R3 small r R4 from the main diagram, we are converting it into the delta connection. So when we are converting it into the delta connection, okay, we are getting this Maxwell capacitance bridge. Okay, so this is the R3, this is small r, this is the R4, this is the capacitor. So here we are having a 3 points, A point, then we are having C point, then we are having E points. Okay, so we are converting this values with the help of star delta values, we are converting into the RAE, means from this A to point E, we are making this RAE. Okay, students. Then we are making the value of the RAE, RC. Then we are making the CE value. Okay, these three resistance values mean this star delta is converted into this delta connection with the help of this diagram. Okay, so RAE is the R3 R. Okay, means when we are talking about RAE from this A point to this E point, okay, from this means A point, we are moving toward this E point. So this is the, when we are moving from the A to the point E, we will find out this resistance RAE when we are going to this point to this point. Okay, so when we are moving from this point A to point E, there are the two resistance. Okay, there are the two resistance. First is the R3, then second we are having a small r resistance. So when we are finding this RAE value, this delta value from this star connection, we will write down this thing R3 and R. These two resistance R3 into R, then in the bracket 1 by R4 plus 1 by R3 plus 1 by RE. So try to understand how I am converting this star delta connection, this diagram into this. To convert this diagram into this diagram, we are using the concept of the star delta connection. And students, in the star delta connection, what we are doing here, we are converting the, like this one is the star connection we are having, this is our resistance, like this is our resistance R3, then we are having a R4 resistance. So kindly see beta this diagram. This is the R3, this is the small r, this is the R4. This is our connection. Here we are having a capacitor. Okay, so this is our like a star connection. Okay, students. So in this star connection, we are having a point. Here we are having point A. This is the point E, and here we are having a point C. So first of all, we are finding the RAE resistance from this one, RAE resistance. Okay, because in the star connect delta connection, we are having like this one. Here we are having one resistance. Here we are having a second resistance. Then in the last one, we are having a third resistance. This is the RAE resistance. Okay. So to find out this RAE, this resistance, we will write down the, this one is the R3. When we are moving from A to point E, we will write down R3 into small r. In the bracket, we will write down the 1 by R3 plus 1 by R plus 1 by R4. We will write down this term. Okay. Similarly, when we are moving from the A to point C, here we will write an R3 and the R4. Similarly, C to E, we will write down R4 and this R in the outside the bracket. Then the inside the bracket term almost same. Okay. So this is our like a star delta conversion. So next, when we will say that our bridge is balanced, like our bridge is balanced when this I1 current, this I1 current is flowing, whole I1 current is flowing through this R2 resistance. Means this detector is showing the null indication. Means V1 voltage is equal to V2 voltage. Similarly, this I3 current is like this IR current. First of all, we are taking this IR current. This IR current is equal to this IC current. Means no current is flowing from this detector, then our bridge is balanced. So I have written here equations. I2 is equal to I1. Means whole current I1 that is flowing from this R1 and L1, it is flowing from the R2. Means I1 is equal to I2. No current will pass from the B2 detector. Okay. So detector is showing the zero indication. No current is flowing. So next, we are having IR is equal to IC. Then I3 is equal to I4 plus IC. So by using this star delta transformation, we are converting the star into the delta connection. Then when we are converting this Anderson bridge into the Maxwell bridge, then in the Maxwell bridge, we will apply the simple formula of the Maxwell bridge. Means we have find out the R1 resistance. Means this is our Maxwell bridge, students. In the Maxwell bridge, we will find out this R1 and the L1. Okay. The same formula which we have derived in the Maxwell bridge, same formula I have written here. Means R1 is equal to R2 RAE divided by RCE. So we are putting this value here and we are getting R2 R3 divided by R4. Similarly, for the L1, we will write down the formula of the Maxwell inductance bridge, and by simply writing the formula, we are finding the L1 values. So we are finding this R1 and the L1 by simply taking the values from the Maxwell inductance bridge. So this is about the Anderson bridge. Now tell me any doubt to any student. So student, this is the next bridge that is called the Hay Bridge. Okay, the Hay Bridge is basically, this is the AC bridge. Okay, means the supply which I am giving here, it is the AC supply. So this is the AC bridge. Second thing, with the help of Hay Bridge, we will find out the value of the L1. Okay, means this is used to measure the value of the inductance. Okay, the second point is that it is used to measure the value of the inductance. Third point, we will measure the value of the inductance in which phase angle is large. Means the inductor which is having the larger phase angle. So this is the Hay bridge, it is the AC bridge. It is used to measure the value of the inductance, and this is used to measure the value of the phase inductor value. This is used to measure the value of the inductance which is having the larger phase angle. So this is the brief about the Hay bridge. What is the Hay bridge is doing? So it is the advantage that it means it is used to measure the inductor value which is having the phase angle large. Means we are having a phase angle tan inverse omega L upon R. If the inductor is having this tan inverse value is large, okay, in that case we are using this Hay bridge to find out that inductor value. Okay, so our bridge is balanced. This bridge, Hay bridge, will be balanced when our, suppose this is the point, I1 current is flowing from this one. Okay, So when our bridge is balanced, okay, so I will mark this is the A, B and the C and the D point. So our bridge is balanced when this I1 current is flowing from this arm B and C, and no current will flow to this detector, means it is showing the zero indication. So whole current will be passed to the I2 R2, means this is equal to I2 is equal to I1. Then our bridge is the balanced bridge. Okay, so our bridge is balanced when our bridge is balanced. Bridge is balanced when I1 is equal to I2, means no current is flowing through the detector D. Okay, so at that point our bridge is the balanced, and our ith current, means if ith current is flowing through the R3 and no current flow to this detector, and the whole current, that is the I4 current, is flowing through this arm. If I3 is equal to I4, means no current will go to this arm detector D, then our bridge is balanced, means I1 is equal to I2, I3 is equal to I4, then our bridge is the balanced. When our bridge is balanced, over V1 voltage, this voltage across the V1 is equal to the voltage across the V4. Okay, so V1 is equal to V3 voltage and V2 is equal to V4 voltage. Mean the voltage drop across this arm and voltage across this arm are equal. Okay, so this is the balanced condition of our bridge. So we will find out the value of the V1, we will find out the V3, V2 and the V4. So what is the value of this V1? Voltage across the arm V1. So we will write down V1 is equal to, uh, we will find out the value of the V1 is equal to I1 Z1. Okay, Z1 is the impedance of this arm. Okay, so we will write down the I1 R1 plus J omega L1. So R1 is this resistance, inductive reactance is J omega L1. Okay, inductive impedance, we can say that the inductive reactance, that is we will denoted by XL is equal to J omega L1. So I have written it. It is in the series R1 plus L1. So we will write down R1 plus J omega L1. Similarly, we will write down the V2 is equal to, we are having a I2 R2, V3 is equal to I3 R3, then V4 is equal to, that is the resistance and this capacitor. Okay, so this is in the, again these are in the series. So we will write down the R4 plus 1 upon J omega C4. Okay, this is our V4 voltage and the current is flowing from the I4. Okay, so we will write down this V1 is equal to this one, V2, V3, V4. Okay, we have write down all the voltage across each arm. Now we will use the identity like V2, V1 is equal to V3. Okay, and V2 is equal to V4. Now we are putting the values in this equation. We are getting like we are getting equation V1 equation is this one, V3 is the I3 R3. So we are equalizing this equation and V2 and V4. We are getting the equations. Student, first of all, you will write down the voltage across each arm. Then we will put these V1 value, V2 value, V3, V4 in this equation. So when we are putting the values in this equation, we are getting like we are getting the equation I1 R2 is equal to I3 R4 minus J omega C4. Here we are having a, when we have written this equation, I have written Z like a V4 is equal to I4 R4 plus 1 upon J omega C4. But here I have written the, like, this is our like a, we have equalizing the equation of the V2 and the V4, but I am writing I1 here, I am writing I3 here, because we have taken I3 is equal to I4. So here I have written the I3 R4 plus, here I have written the plus sign, but here it is the negative sign. Here is the iota like J. If I am dividing here, dividing the, multiplying the and dividing this equation by J, it will become the J square. It will be the J. So it is the R4 plus J upon J square omega C4. J square is the minus 1. So it is the negative sign here. So I have written this equation. Okay. So I have written this equation. V2 is equal to V4. And we are having a second equation like R1 plus J omega L1 upon R2 is equal to R3 R4 minus J omega C4. So how this equation will become? We are having first equation, this one. Now we will write down the equation. Second, we are having a R1 plus J omega L1 I1 is equal to, this is our V1 voltage, that is equal to the V3. We are having like a I3 and the R3. So this is our first equation is this one. Second equation is this one. When we are dividing the equation number second by the equation number first, okay, we are getting the this equation. So this is V1 is equal to V3. This is the V2 is equal to V4. So when we are equalizing these voltages, we are getting this resultant. Okay. So when we are dividing the equation 2 with the equation 1, we are getting this equation. Now cross multiplying these equation, then separating the real and the imaginary parts, we are finding the value of the R1 and we will find out the value of the L1. This you have to, this exercise you have to do by their own. This is simply you will do the cross multiplication of this equation and then simply separating the real and the imaginary parts. You will find out the value of the R1 and the value of the L1. So what is the value of the R1 and the L1? R1 value is the omega square C4 L1 R4 and L1 value is the R2 R3 C4 1 plus omega square C4 square R4 square. So this is the value. Last, when we are separating the real or the imaginary part, you will find out the value of R1 is this one, L1 value is this one. So this is about the Hay bridge. Any doubt to any student regarding this?